In this video, we're going to talk about how you can test random effects and then also talk about robust methods. Testing the significance of random effects is a bit different than fixed effects. And before I move on, I wanted to ask if anyone recalls the main reason for this. And so I'm going to just hold off a second here, or you can pause the video briefly, and then I will show you the answer. The reason is that variances are constrained to be greater than zero. Therefore, the normal distribution, or t-distribution, are not appropriate for conducting tests because these are not constrained distributions. They can be less than zero. LME4 provides two methods for estimating the confidence intervals of variance parameters: parametric bootstrap and profile. There's also the walled method available in LME4, but this is only applicable to fixed effects because it is a z-test-based confidence interval. And profile is the preferred method and the default method for constructing these confidence intervals. It's based on the log likelihood computation of the model. And so it's a little bit similar to a likelihood ratio test, but not exactly the same, as we'll discuss briefly. And so this is the preferred method for testing the significance of the random effects. And so you see here when we call the confident function, profile is the default, and we get these confidence intervals. And as long as these don't include zero, then we determine that these variances are significantly different from zero. And we can also likewise use these methods for confidence intervals for the fixed effects. Another alternative is the bootstrap method. And we can call this with the method equals boot, but this is both probably often going to be slower and not necessarily have any advantages to the profile method, so the profile method is still preferred. And as mentioned, the walled method won't even provide confidence intervals for the random effects, although it will provide them for the fixed effects. We also have talked about doing likelihood ratio tests for random effects, and we can do this with the rand function. However, it turns out that this is actually not recommended, and the reason is that the likelihood ratio test is not appropriately chi-square distributed when the null hypothesis is at the boundary of the parameter distribution. In this case, our null hypothesis is that the variance parameter equals zero, and the boundary of the variance parameter is zero. So the null hypothesis is exactly the boundary of the variance parameter. So the chi-square test is not, or the likelihood ratio test is not chi-square distributed and can't be appropriately tested with a chi-square test. So this is not truly a recommended method. See the lecture slides for more details about this. And just for reference, this is what you can do, and you will get an output. We've talked about this in previous labs, but once again, this is not recommended. Just use the confidence intervals, and in particular, the profile confidence intervals. And the last thing we're going to talk about for this lab is robust methods. So all of the methods that we've discussed so far for all of the estimations and tests that we've performed have assumed homogeneity of variances within each cluster. So essentially, the assumption is that the variances for each cluster around the cluster mean are the same for all clusters. Robust methods can help when this assumption is violated and can also help if the normality assumption is violated as well. So we're going to discuss two robust methods, the sandwich estimator, which produces robust standard errors, and then the design data scale method, which actually provides robust parameter estimates, not just standard errors. The parameters package provides options for the sandwich estimator for estimating robust standard errors. It should hopefully install these other packages as well as dependencies. For me, it did not, and I had to figure out what was going on, but you need all of these packages loaded up or at least installed for the parameters package to function and correctly apply the sandwich estimator. So if it doesn't work, you may want to try installing these packages as well. And then this is how you call the robust standard errors in the parameters package. So the function is model parameters. You need these vcov type, and vcov args method, vcov args arguments. So vcov estimation, vcov type, vcov args. These two you can always set to CR and CR1. The vcov args needs to identify the cluster identifier. So it's list and then cluster equals your cluster identification variable. Then of course you want to set robust equals true, and you need to specify your degrees of freedom method, and in this case, Sater weight. And so this is the way the output looks. The table looks a little bit different. It's actually cut off a little bit here in the end. I think this isn't cut off in the PDF version, but it is in the HTML version here for some reason. And so note that the only difference between this and what we've looked at is the standard errors. The parameter estimates in the coefficient table are the same. And then we get our Sater weight degrees of freedom, our t-statistics, and our p-values. And we could actually use this same model parameters function to get our non-robust results, if you like the way that this table format looks. And we could also use it to get the degrees of freedom adjustment without Elmer test. So this is just a regular LME4 model, and we can use the model parameters to get the Sater weight degrees of freedom. It's just an alternative method. And if you compare these first two columns to what we just looked at, note that the coefficients column is exactly the same, but the standard errors column is a little bit different, with the robust method having slightly larger standard errors for intercept and active. But our results in terms of inference testing don't change. The other approach is the design adaptive scale estimator, and this is provided by the robust LMM package and the R-Elmer function. There are two methods available for design adaptive scale. They're called DAS tau, which is the default. And according to the help page, this will typically be slower but a bit more accurate. And then there's DAS var, which will typically be faster. And it will also be the only method available for more complex models. Interestingly, when I ran both of these, I got a faster output from DAS tau, so I'm not quite sure why that is. But again, this is just sort of repeating what the help page for this function said. So here I install the package, I load the package, and I'm calling system time on my model fit. So inside the system time, I'm just creating my R-Elmer object, and the reason I'm doing this is because I want to see how long it takes for it to go. It took about 20 seconds for this function to work on this model on my computer. And here we see we actually get not just different standard errors, but we also get slightly different parameter estimates. So if you look at the active and intercept estimates here, the intercept is 3.83, active is 0.548. And if we go back a few slides, we see that these are different from the parameter estimates that we got from the non-robust methods and even from the sandwich estimator methods. So this estimates robust parameter estimates, not just robust standard errors. Now, one issue that we've already seen is that the R-Elmer approach will not give you the degrees of freedom adjustment. It's similar to LME4 in that way. And there actually isn't an Elmer test analog to give you the degrees of freedom adjustment. So one thing we can do is extract them manually from the Elmer test version of our model and then sort of smush them together to get the appropriate degrees of freedom and get p-values. If we want, we can just think of these t-values here as being z-statistics and not worry about it if we assume our sample size is large enough. But if we do want to get the degrees of freedom adjustment, we have to pull them out of the Elmer test version. And then what we do is we take the t-statistics from our robust method, which is here. That's what this is calling. And then we're getting the degrees of freedom from our non-robust method. And then we're just doing a t-test on them, which is what this function does, multiplying by 2 to tell it a two-tailed t-test. And that gives us our p-values and degrees of freedom. So we can do our actual t-test, and we can just sort of smush everything together on our own by creating a data frame where the first column is the coefficients from the robust output, The second column is the standard errors from the robust output. The third column is the t-statistics from our robust output. The fourth column is the degrees of freedom from our non-robust output. And then the last column is just these p-values that we computed on the last slide.